but they're not. There is an enormous practice, infectious disease surveillance is going on all about us, all around the world, for a huge variety of infectious diseases all the time. There is a theory, it's fairly basic statistical theory for designing sampling systems and designing surveillance programs in that sense. But there is very little attention paid in that theory to infectious disease dynamics, very little attention paid to surveillance by the sort of community represented in this room. Now, I hope I don't have to convince anybody here that infectious disease surveillance is important. It obviously provides the raw material, the raw data, certainly at the population level, which we use to understand the dynamics of infectious disease, that we use to inform the design of control programs and prevention programs and so on. I mean, that's the basic currency with which we work. If you still don't believe me that it's important, there are lots of very high-powered reports saying how important it is. I've been involved in some of them. Foresight program from a few years ago in 2006 said all this, trying to make diagnostics and surveillance give it a higher profile. There was a report commissioned by the Institute of Medicine in the US a few years ago as well on surveillance for emerging zoonoses. So everybody's agreed it's important. But is it interesting? Not everybody seems to convince. The scientific community has not picked up on the issue of designing surveillance programs and surveillance systems with quite the same enthusiasm they picked up with a lot of other problems related to our area. And clearly, if in 30 minutes' time this seminar room looks like that picture, I will have failed in this particular attempt to make it interesting. Nonetheless, I think it's sufficiently important that we should be paying some attention to it. So the way I'm going to structure this talk is to give it a narrower focus and to describe some recent steps towards developing what some people refer to as smart surveillance systems, which simply means using information on patterns of risk of infection to design more efficient surveillance systems. More efficient means getting the same amount of information out, this is after all an information gathering exercise, for less effort and at lower cost. And the topics I'll use to illustrate that, it's a bit of a mismatch of different approaches. Foot and mouth disease, hospital-acquired infections as examples of targeted surveillance and where people are working in that area. Surveillance against noisy backgrounds, so using the examples of influenza in poultry and in people, and detecting unusual events, emerging infectious diseases being the obvious motivation for that one. But there's a common theme. And the theme is throughout this to use model-based approaches, models of infectious disease dynamics, to help design your surveillance system. And that's the theme I want to emphasize throughout. And the reason that seems a sensible thing to try and do is, of course, looking back 20 years and beyond to these gentlemen and many people represented in this audience too. We have an incredibly well-developed theory for infectious disease dynamics at the epidemiological level. Not perfect, lots to do, but it is very advanced. And we have turned this theory to the problems of understanding dynamics, understanding control and prevention, but we have not applied it to designing surveillance systems. So let me give you some examples of where that has been done. So here's an example from my own group in Edinburgh from a few years ago. Ian Handel was leading this. And the question that Ian was interested in was a very specific applied one. It was about establishing freedom from disease after a foot and mouth epidemic has occurred, in this case motivated by the 2001 epidemic in the UK. It is an international requirement that you establish disease freedom. To do that, you have to do surveillance. You have to test a whole lot of farms, see if disease is present. You do that within a pre-designated surveillance zone, and at the time, anyway, the requirement was that you reach this 95% system sensitivity. So what Ian has done on this is an EU requirement. So what Ian has done on this is for a particular scenario, parameterized for Devon in England, is shown that to do that, using the sampling system they would have implemented, you need to look at about 1,000 farms to get the required surveillance system. And that is in practice more or less what was done. But he thought you could do better. So he took one of the ever-growing suite of spatial explicit microsimulation models to look at the spread of foot and mouth disease, ran those, produced cases, but then layered onto that a model of the diagnosis and detection of foot and mouth disease to look at the risk of non-detection on an individual farm. And what he got was a map like this. This is Devon, and this is a sort of risk map most of you will never have seen before, because it's the risk that there is undetected infection still present on those farms on the basis of those two models. So using that information, he can design a targeted sampling strategy where you look at the highest risk farms first. Very sensible thing to do. Oh, sorry, wrong. There we are. And then you get a performance curve like this. So your risk-based strategy is detecting or reaching your system sensitivity with 95% for a much smaller number of farms. In fact, it's 5 times more efficient. And that's a real gain. This is what would have happened in practice, more or less, and this is what you could do with an ideal system. So it's an enormous gain in efficiency just by doing risk-based targeted surveillance. More recently, we've been looking at a similar sort of problem in the context of hospital-acquired infections, motivated mainly by MRSA, but not exclusively so. And we've been looking at network dynamics, and this is work originally done by Mariana Ciccolini and picked up by Bram von Bunnik now in Edinburgh. And this is a map of the network of hospital movement. So we're interested in MRSA or any pathogen that is spread between hospitals, mainly by patients moving from one hospital to another. It's a very typical sort of network. You can see some major hubs here in Glasgow and much more peripheral institutions elsewhere in Scotland. And what Bram's done, and Bram and Mariano have done, is put a stochastic network SI model on that. It's SI because this is a relatively short time scale and we don't think hospitals recover, if you like, from MRSA infection. They get it and it becomes established quite rapidly. Well, there's more to say about that, but this is the simple model. And we get this, or Bram produced this quite nice heat map. So this is the time to infection in individual hospitals ranked from those that get it in most simulations, or on average during the simulations first, and those who get it much later. And you can see there's a concentration of hospitals down here that are very likely to get this infection early on in the course of an epidemic. Incidentally, we can test this model, or validate this model to some degree against actual data. So this is also, in some ways, a measure of risk of having MRSA infection or acquiring it during an epidemic. And we can compare that with hospitals that do, and it's extremely good at predicting the right hospitals. And perhaps more importantly, the network model is better than any of the other risk factors, including simple things like size or number of patients and so on, that we've been able to use. So it's actually a very good predictor of where MRSA is likely to turn up in practice. So then what we can do is rearrange the data. So this is showing the increasing number of hospitals included in a surveillance system and quantify the time to detect MRSA depending on how many hospitals you have included in your surveillance system. And we've got a number of algorithms for ranking those hospitals. The key ones are random and a greedy algorithm, which is probably about optimal, but but probably about optimal. But there's a variety of other ones based on various network and demographic statistics that perform almost as well. And the same sort of thing as we saw for the foot and mouth disease model. If you want to specify a particular time to detection, here it's about 5 months. Using the targeted approach is 6 times better than using the random approach. And this time that's probably not a real effect because you wouldn't use a random approach in practice. In practice, in fact, the surveillance effort tends to be concentrated in the larger hospitals, so actually it will tend to follow that curve. So from a public health point of view, I think the most important part of that graph is the very rapidly diminishing returns. So having recruited your small number of very large hospitals, you don't gain an awful lot by replicating that effort in all those smaller institutions. Looking at a few large hospitals for most practical purposes is probably enough. You can also do the same graph in terms of the number of hospitals affected. So if we're trying to limit it to 5 hospitals that the pathogen spread to before we detect it, well, now it's 8 times more efficient to do the targeted surveillance as opposed to a random one. So again, enormous increases in efficiency. I don't really have time to do this, but I can't really resist it. Very recently, in the last week or two, Bram has been looking at a more complicated scenario. So MRSAs are not all alike, and in particular they carry different antibiotic resistances. In fact, over time, they tend to accumulate them. They accumulate yet another antibiotic resistance. How are they going to do that? Well, they're going to do that by being present in a population of patients in a hospital, perhaps, where they can exchange antibiotic resistances. So different strains have to meet. So this plot here, the black line, is very similar to the ones you saw on the previous graph. That's the time to detection, if you like, for individual hospitals using, in fact, the greedy algorithm that you saw before. But what happens if you apply the same approach to finding 2 strains occurring in a hospital so that they might acquire extra resistance? Well, don't worry about the height of this curve. That's not relevant. It's the shape. Everything is even more concentrated to these bigger hospitals. These sort of events are much more likely to occur and much easier to pick up in the very biggest, well, best connected hospitals. And very rarely anywhere else in the system. So you can do quite a lot more, I think, with this sort of model. Okay, moving on from efficient surveillance to a different kind of problem, but still one that requires models, I think, to shine a light on it. The problem of detecting an event against a noisy background. So this is some relatively old work now led by Nick Saville in Edinburgh from a few years ago. And what Nick was interested was detecting highly pathogenic avian influenza, motivated at that time particularly by H5N1 bird flu, in commercial poultry flocks. So these are a large population of birds. What you would do normally is you would detect an HPAI simply because more of your birds die than you're expecting. You're looking for mortality clusters against a low but measurable background mortality rate, so a noisy background. To make the picture more complicated still, the argument at the time was whether you should vaccinate these flocks to protect them against HPAI. So this is the fraction of birds protected by a vaccination program. Vaccination is a good thing in many respects, but one of the problems is it masks clinical symptoms. The birds don't die anymore, so you can't detect the mortality clusters. So you can look at the probability of different outbreak events happening under these different settings. So what Nick did was write a quite detailed within-flock individual-based model of poultry and commercial flocks, and then superimpose this background mortality on it, and looked at the probability of an outbreak occurring, and that's a very expected curve. As you reach high levels of coverage, you more or less get herd immunity or flock immunity in this case, and you don't get an outbreak. But also the probability of this outbreak being detected, and that rises very rapidly as the outbreaks become smaller and smaller, as you're entering this critical transition, which I think I just entered, didn't I? Here, the probability becomes smaller and smaller that you will actually detect it at all. Put those together, and forgive me for going into some detail here, but it matters. What we've actually drawn here is a curve that shows the probability that you have an undetected outbreak at the very end of the cohort's life. This is something to do with the demography of poultry, but the reason is all the action happens at the end when the birds are cleaned out and replaced, and that's when you have the biggest risk of onward transmission. And what you find is that 80% levels of protection, you have this big spike in the probability you've got undetected HPAI in your flock, which is a very bad thing. And it's a very unfortunate thing because that's almost exactly the levels of coverage you would expect from a vaccination program, levels of protection you would expect. The coverage, the coverage is the problem. The vaccines are very good at protecting, but vaccinating thousands and thousands of birds efficiently is technically difficult, and that's the sort of levels of protection you'd achieve. So a very bad and unexpected outcome from vaccinating in that context. Fortunately, there's a solution. If you put in sentinel birds, few numbers that you watch for mortality, it solves the problem, and you can avoid that spike in detectability. So a nice example, I think, of a counterintuitive kind of result, an important one that's revealed by mathematical models and not by conventional ways of carrying out surveillance. Let's move to a more difficult problem then, but in the same theme of detecting outbreaks against a background, and look for detecting pandemic influenza, which we're doing in Scotland as everywhere else in 2009. In this case, against a background of seasonal influenza that looks like that, trying to use a system called Service, which is a GP-based sentinel surveillance system. So the GPs phone in weekly reports of the number of influenza-like illnesses they have. So can we detect signal from noise in that data? Can we detect a pandemic happening? This is published work that was led by Brajendra Singh, so I'm not going into the details, but having tried an awful lot of different alternatives, Brajendra came up with an algorithm we call a spatial weekly case ratio, which is simply asking the question, is there an increase in the number of ILI cases, and is that increase simultaneous in different areas of Scotland? And that's an unusual pattern for seasonal influenza, so we can use it to try and predict a pandemic. At the time we did the work, we didn't have a pandemic. So we simulated one. In fact, very kindly, Neil Ferguson simulated one for us based on his individually based microsimulations, spatially explicit microsimulation model. So he simulated some pandemics. Those are very precise, so the individual patients that get ill in Neil's model have a postcode. That means we can match them to the GPs, the real GPs that we would have got in Scotland, and when they would have turned up in our surveillance system. So we can do all that filtering and see how our system performs. And it's not too bad. This is the signal of a pandemic on a couple of runs, and typically we can detect it within 4 or 5 weeks of it actually appearing in Scotland, and within 2 weeks of it actually appearing in any of our a single case appearing in any of our surveillance system. So it's a pretty good performance. We can compare that with some of the many other algorithms that people use. That's ours with the simple thresholds, there are Q-sums. There's a whole range of incredibly complex and sophisticated algorithms that people use. It comes out of things like the quality control literature and so on. So there's a lot of statistics available for that. And we can look at different case reporting rates and different specificities. And however you look at it, Bragendra's weekly case ratio performs as well, if not better, in terms of sensitivity or mean time to detection. The interesting bit, of course, is having set all this up, we actually got a pandemic, which was a fairly remarkable coincidence at the time. So let's see how it performs. So this is our weekly case ratio, and this is some of the other measures. Along comes the pandemic, and we didn't pick it up using this system for 12 weeks. Useless. The other ones weren't any better either. So what went wrong? There was obviously some interesting mismatch going on. Well, the main thing is the beginning of the pandemic in Scotland was not one coordinated event at all. It was a whole series of minor, disconnected, asynchronous outbreaks. And coupled with that is the actual pandemic had a considerably lower R0 than the ones we'd used when we simulated it. And those two things, of course, are actually not independent at all. Even so, we actually came surprisingly close using Bragendra's algorithm. That was very nearly a low-level alert that came quite early, and that actually corresponds to one of the larger failed outbreaks that occurred in Glasgow. And we understand the dynamics now a lot better, so we know what went wrong. We know that there was quite a long lead-in period of these small, isolated outbreaks before the pandemic really took off in Scotland. We'd done the sequencing, we did real-time sequencing, so we know that those small isolated outbreaks had different origins. Most of them came from North America. The one that took off actually did come from England, but the initial introductions were from other parts of the world, so we know that. And we can model it as well. And we can model the fact that it takes pandemic influenza quite a long time to take off in Scotland, which is mostly determined simply by when it first hits a school. And if it doesn't hit a school early on, it tends to go extinct. We've got some nice models capturing that sort of behavior. So at the very least from that exercise, we've learned a lot about what was different between a real pandemic and our simulated one, and that of course will feed back into how we might design more effective surveillance systems in the future. Another brief aside that I can't resist doing, because I know serosurveillance was mentioned a couple of times yesterday, is also with enormous difficulty in practice. We set up a real-time serosurveillance system during the pandemic and got serological data, estimated prevalence of infection rising over the course of the epidemic. And that's useful information, but it's difficult to interpret because at the same time you've got a vaccination program, which is vaccinating different age groups at different rates, and the number of vaccinated people is accumulating in the population at the same time as the epidemic is, or the pandemic is going on. So we wanted to try and divorce those, which we did using quite sophisticated Bayesian analysis led by Ian Handel. The first Rothman paper was Nigel McLeish, and fitted basically falling force of infection curves to different age groups. Now that gave us one of the first estimates at all of the actual number of natural infections, which is about just over a third of the Scottish population exposed, so that's very valuable data to have. It also, incidentally, gave us an estimate anyway that 1/3 of the people that were vaccinated in Scotland had already been exposed. That's a population-based estimate, but it's an important number because, of course, vaccine production is often limited in the stages of a pandemic, but also vaccine delivery is difficult as well. So we're wasting an enormous amount of effort if we're already vaccinating people who have been previously exposed. And that, I think, is a very good motivation for developing basically rapid GP-usable diagnostics to find out if people have already been exposed. And that's some ways down the track, but it seems to be a useful thing to do. So what have we learnt from those two studies? Well, not surprisingly, anyone interested in surveillance will always call for better data, but in this case it's practical, I think. So Scotland has now changed its GP Sentinel system from the few dozen GPs that were reporting before to the hundreds that are actually needed. Ideally, we'd like to move to daily reporting. We'd like more reliable reporting. GPs do seem to fluctuate in their enthusiasm for reporting ILIs, so it's quite difficult data to know. And we absolutely do need serosurveillance data because that provides us with information that simply can't get by any other method. I put better pandemic models, but that's probably not quite fair. Probably what we needed was a more appropriately parameterized pandemic model, and we need to consider those sorts of things. And we need to understand the early stages of a pandemic, perhaps in more detail than we'd paid attention to previously. And ultimately, we would like to have clever algorithms. Our spatial weekly case ratio is perhaps a marginal improvement on the ones that are already available, but perhaps it's possible to do better. So pandemic influenza is a novel strain of a pathogen, but we're also applying these same sort of techniques to look for novel pathogens of all kinds. This is centered around a large Wellcome Trust funded program called Visions, which is based out of Vietnam. Until very recently, it was led by Jeremy Farrar. We have a slight problem because Jeremy Farrar has now moved on to greater things and has left us leaderless, but we'll do our best to carry on without him. And two of the things that we're looking at that are relevant for this talk are disease burden, infectious disease burden in hospital patients and also in a high-risk cohort. That's people in direct contact with various kinds of animals, both domestic and wild, and applying outbreak detection algorithms to those sorts of data to see if we can pick up these unusual events. There's a whole raft of other things we're trying to do as well, but those are the ones that are relevant. The Vietnam hospital data comes from 5 provincial hospitals, so these are scattered right along the length of Vietnam, and we're doing proactive surveillance in those hospitals looking for individual cases, but many of them all very kindly release their historical data. So we have data on something like 250,000 infectious disease admissions over the last 5 years, and which we can categorize according to the infectious disease that was diagnosed. And the important thing about this pie chart is an awful lot have this unknown etiology. Now, that doesn't mean that they really are unknowable or novel. It simply means that no effective diagnosis was made. That's not untypical. Vietnam's not untypical. That would be the case for a lot of hospitals in Europe as well, that we don't actually get a specific etiology from many of the cases. But nonetheless, that clearly represents a very rich hunting ground for novel or unusual events. And we've been just started looking at the data. This is with Maya Rabba, who recently joined us, and looking in a province called Dak Lak, which is in a remote mountainous region of Vietnam and is relatively understudied in this regard. And the first thing she picked out, simply by visually inspecting the data, was a very odd pattern to do with dengue. Dengue fever is very well known in Vietnam, but in Dak Lak they have a very different pattern, and the diagnosis seems a little bit different. So clearly that's a place that we should start looking. We would, however, like to do better. One way to do better, or a path to doing that, is pointed out by Tiffany Bojic and colleagues from a very nice paper a couple of years ago. Well, they used a network analysis to classify infectious disease outbreaks using a variety of information, both epidemiological and clinical. In this case, it's different encephalitises. And what you can see is those different encephalitises cluster quite nicely into recognizable groups that we can put names to. But importantly, these white ones here are outbreaks that did not have a name attached to them. Remember, I showed you that that's very commonly the case for individual patients in Vietnamese hospitals. And roughly, I believe it was 30% of those did not all obviously classify with some of the existing outbreak classifications. So that seems to me a very powerful approach, again, for highlighting these individual events that seem out with the normal run of expectation and simply merit further investigation. And that's something we'd like to take forward in our work in Vietnam. Finally, just stepping up to the global scale, is infectious disease surveillance carried out to the best effect globally. What this is a map that was published in the Institute of Medicine report I referred to right at the beginning, which superimposes on one of Kate Jones et al.'s hotspot maps, a slightly updated one, of where emerging infectious disease events are most likely, the locations of the kind of diagnostic laboratories that look at zoonotic disease and would be able to pick up, at least we hope they'd be able to pick up, unusual emerging disease events of the various kinds that have been mentioned in previous talks. And the obvious point about the graph, they're in the wrong place. They're not mostly in where the hotspots are. So there's a clear call that we need to increase diagnostic capacity in other parts of the world. That's a risk map, but actually it's validated by any kind of summary of the data, and Emily Chan from John Brownstein's group did a nice paper on this a few years ago, just plotting out outbreaks that were reported through the various WHO and related systems, and that confirms the hotspot map. These aren't emerging infectious disease events per se, but they're unusual outbreaks that we would like to see investigated. They are definitely in the wrong place. So there's a major motivation there for seeing about coordinating a more globally appropriate distribution of diagnostic effort in order to try and detect infectious disease outbreaks early on. So what do we conclude from all this? Well, the risk or the distribution of infection is, we all know this, very heterogeneous in populations. And that means when you're trying to gather information on those infectious diseases, targeting works. So smart surveillance is almost always going to be more efficient, I would conjecture. It's much more efficient in terms of foot-and-mouth disease post-epidemic. I said about 5 times more efficient, 6 times more efficient for detecting hospital-acquired infections that are newly emerged. We might be able to use related kind of techniques for faster outbreak detection. As I showed, that wasn't an entirely successful exercise first time round, but I think it merits further attention. And we can certainly use these sort of techniques to prioritize our investigation and detection of novel infections and novel outbreaks. Don't look too sleepy at the moment. It certainly doesn't look entirely like that picture I showed at the beginning. So hopefully, at least some of you would agree that designing better surveillance systems is actually a challenging problem for modelers and quantitative biologists. This is the sort of work that we could reasonably try or think about undertaking in the future. And it's an interesting set of problems. And it is important because more efficient surveillance is our first line of defense, and ultimately it's going to lead to more effective interventions. Thank you very much. There's a whole lot of people who have contributed to this work. I've mentioned most of them, I think, as I go along, whose work I referred to, but there's a long other list, and I should mention some of the funders, in particular actually the EC program FP7, which funded the hospital-acquired infections network work. Thank you very much.
I was wondering if you think there's any cases when targeted surveillance doesn't work, and I was thinking particularly about bovine TB in Britain, where targeted surveillance, or whether you think targeted surveillance works here, and about the edge areas where targeted, by directing testing towards the high-risk areas, kind of miss the expanding edges.
Right. There is, I think, a very difficult area of theory is exactly how you optimize where you look to detect a disease. So I'm going to broaden my answer beyond your very specific context. But it is this. You actually want to look where there's most uncertainty. So looking where there's a very low probability of disease doesn't provide you much information, but actually also looking where there's a very high probability of disease doesn't provide you with that much information either. The important thing is to target the areas of maximum uncertainty, and that simply, as far as I know, isn't done. I think that's an untouched area, but I think it's relevant to your problem. Too many.
When you talked about surveillance of hospitals for acquired disease, you mean you want to test all patients at the large hospital, or how would you do that within a hospital?
So that's the infection control units in the larger hospitals are very much geared up to looking for MRSA variants, Klebsiella, Clostridium, and so on. So they have the diagnostic capacity in situ. What happens with the smaller units is that they don't have it in situ. So if they have cases they want to investigate, they have to refer them back. They tend not to do that, and most of the diagnostic effort gets concentrated in the hospitals with the facilities to do it. So the question is, how many hospitals do you need to invest in that sort of capacity? And our argument actually probably isn't that many in practice. That's not a very good answer to your question, but try. Simon.
I think surveillance systems like the GP data are very biased by presentation, people presenting to healthcare. And in England and Wales, we saw a lot of that because everyone was terrified of swine flu, and so presented in July 2009. Going onwards, how do you think you can correct for those sorts of biases that end up in most passive healthcare systems and keep it sustainable?
Well, the first thing is what we're doing, and actually, in a sense, John was sort of doing something along the lines, is simply looking for patterns in the present that we haven't seen in the past. And that's what we're looking for. And the interpretation of those patterns requires in itself further investigation. And it may indeed simply be changes in reporting behavior. That's entirely possible, and that should be on everyone's list when they see something new. So it's about detecting something new. Now, the questions you could ask and could use models to address, expanding on, say, the work that Rajendra did with Neil's model, is say, well, what sort of changes might we expect given particular scenarios? What signatures do those have, and can we include those in our repertoire of things to look at? Do they have particular signatures? So that's always what you're looking for. I must admit, I'm approaching this on a fairly theoretical basis. Nice contrast, I think, to John, who was coming at, on a practical basis, to John, who was coming at it from the theoretical direction. I think somewhere in the middle is probably the optimum approach for doing this kind of analysis.
Yeah, just sort of following on from the practical side of things. I mean, are there instances where sort of risk-targeted surveillance becomes difficult to do in practice because, for example, a hospital or a farmer might say, why do you keep coming here and testing me as you're not testing these other people, my competitors or these other people down the road? And another example might be the Police Complaints Commission and stop and search. Should you be using your methods to sort of advocate them stopping certain ethnic groups more often than others, for example?
Well, if I knew the answer to that, I guess I'd be writing letters to the Guardian rather than speaking here. I mean, you're absolutely right. It's a difficult problem. I have to say, my very narrow experience in that field of working with individual farmers and individual patients on the ground is people actually are quite understanding of why scientists are motivated to do research. I personally not encountered those sorts of problems. Some of the communities I work in, people actually quite like being researched in that sense. So that's my very narrow personal experience.
Mark, they don't like the consequences of it, though. They don't like being restricted and having their businesses interfered.
No, that's absolutely right. I'm taking the easy way. I'm just concentrating on getting the information, but you're spot on. What is done with it may have adverse consequences. But I mean that applies not just at individual farmer level. That applies to the global surveillance systems that we were talking about in the Institute of Medicine report. I mean, clearly there are very strong disincentives at the country level for reporting. I don't know if Chris covered this yesterday, but it's a key point. Yeah.
So I think that was wonderful session as well. Thanks very much to Mark and the others. But to keep to time, I think we'll stop the tea now.